thank you all for being here, and please give a warm welcome to Professor Johan Rockström.
Thank you so much, and it's a great pleasure and honor to be here at the Fritz Institute to give this inaugural lecture in this very important series. What I'll be doing is trying to give a state-of-the-art scientific overview, and based on this, then share with you some thoughts on transformational and exponential roadmaps towards a safe and just future for humanity on a stable and resilient Earth system. And I think that it's an appropriate start to kind of connect to the introduction here to make clear that, yes, we are living in real turbulent times. This is no doubt a time when we both geopolitically but also environmentally and justice-wise around the world are starting to see shake-ups on both Earth system changes combined with socioeconomic injustices that are starting to show something really important, which can be summarized in a way, both scientifically but also emotionally, which I think is best done, to a large extent, through the first pictures of Earthrise, which, in my mind, summarizes large parts of our challenge today. That when we look down at planet Earth, we start to realize, just by this visual, that this is a very small blue marble in a very, very kind of marginal corner of the universe. And last night I had the privilege of giving a talk at the Republica session here in Berlin, followed by your very famous German astronaut Alexander Gerst, who could kind of testimony to the fact that this is a mind shift of seeing Earth rise from space, which in a way you could argue that because not all of us have the privilege of doing that, of being out in space and having a look at our little small marble home, perhaps the only way for us to kind of get the equivalent experience is to talk and listen to science. Because science is really trying to understand how the Earth system operates and what will it require for us as a species, as humanity, to have a just and safe future on planet Earth. And if there's anything that is the red thread through this talk, is that we have very recently, I will even argue just over the last few decades, tipped over from being a relatively small world on a big planet, which is the way we've been operating as human beings on this planet for the last 100,000 years as modern humans. And it's just over the last few decades that we've tipped over and are now the relatively big world on a small planet. The planet is very small. We've filled up all its space. We've reached a saturation point. We're starting to hit the biophysical hardwired ceilings of the capacity of the Earth system to cope. This is the moment when we need to transition. Actually, a way to kind of give you a summary and starting to the end is that we have, I would argue, unequivocal scientific evidence actually, with zero uncertainty, that it's over the last 50 years that we've changed conditions on Earth as they've been over the past 10,000 years, when we left the last ice age. This is the moment of the great acceleration. These are the hockey sticks of exponential rise and pressure on the Earth system, from everything from greenhouse gas emissions to land degradation, deforestation, air pollution, heavy metals and microplastics. We're loading the Earth system in an exponential pressure. That's unequivocal. But I would also argue that there's rising scientific evidence that's in the next 50 years that we will determine the outcome for the coming 10,000 years. So this proves that we are on a knife's edge. It is now the moment of decision. And many of us, I can see in the audience that that does not apply to all of us, but it actually applies to me. I can raise my hand and admit that I am part of the culprits. I've been part of this 50-year journey that took us to where we are today. And if I have good chance and good health, I may be actually alive for parts of the decades into the future that will determine the outcomes for all future generations on Earth. So this is not only the moment in time, it is up to us, the adult generations living on Earth today, that have caused the problems that has taken us where we are, that now need to solve the problems for the future of all generations on Earth. That is why it's such a decisive moment. And I would argue that we have so much scientific evidence that this is the time. In fact, it's so sharp that even the careful and importantly crafted Intergovernmental Panel on Climate Change, the IPCC, as you may remember in the 1.5 degrees Celsius report, what I would argue is the most important scientific report ever released, just last year pointed out that we need to bend the global curve of emissions within the next few years. Christiana Figueres, who led the Paris Climate Agreement, who took us successfully to the legally binding Paris Agreement of staying well below 2 and aiming for 1.5, has, as you may know, devoted all her life after leaving the head of the United Nations Framework Convention on Climate Change, the UNFCCC, to devote all her life to Mission 2020, to try and do everything she can to mobilize support among all nations, among businesses and cities, to bend the global curve of emissions no later than 2020. That was kind of conclusion 1 in the IPCC report. Conclusion 2 was we need to cut emissions by half over the next decades. We have 10 years to cut emissions by half. So when you've heard science stepping out of its comfort zone to say this is the decisive moment, this is the decade when things have to transition, this does not mean that planet Earth is falling over some ultimate escarpment, but it does mean that now is the time to change direction, and we only have 10 years to do it. That is why I would argue that this is the moment to act. This is the moment we have to really move the dial. Now, the evidence, of course, behind this is a long, big story of complexity, and I'll really try to walk it through together with you. But the simple starting point is, of course, the graph that we all now are too familiar with, the hockey stick of temperature rise on Earth. We have pushed up temperatures with 1.1 degrees Celsius compared to the average 14.5 degrees Celsius and the pre-industrial average on Earth. We know that the 4 last years are the warmest observed temperatures on Earth since the Industrial Revolution and since observations started. This was verified by the World Meteorological Organization just in its latest report a few months back, that this is now established. But not only that, what this report also points out in the furthest down conclusion here is that 1 degree Celsius warming is now verified, but it's also that this is the warmest temperature on Earth since the last ice age, meaning that we have truly bumped into the ceiling of the maximum variability of temperatures since the last ice age. So this is a reminder that we've really reached a point of saturation. Now, this is already starting to show significant impacts. So already 1 degree Celsius warming is leading to, as we all follow closely in media today, kind of a rampant acceleration, amplification of extreme events. I would even argue that we may be looking back at 2018 as the first year when the Earth system started to send invoices back to the economies across the whole planet. You remember it started with the forest fires in California, the devastating heat wave and floods in Japan, the Kerala flooding, the Philippines flooding, right now basically still with the aftermath of the cyclone Idai in Mozambique and Zimbabwe, but also the record temperatures, 51.2 degrees Celsius measured, the warmest temperature ever observed on Earth in North Africa last year, minus 50 degrees Celsius in Chicago just a few months back, and plus 50 degrees Celsius at the same time in parts of Australia. These are natural variabilities that we've always had, but that we can no longer disconnect from anthropogenic global warming, meaning that there is a connectivity of amplification of our greenhouse gas emissions causing global warming, amplifying and reinforcing extreme events. To this comes an equally challenging dilemma, potentially even more challenging, which was released just 2 days back with the International Panel, the Intergovernmental Panel on Biodiversity and Ecosystem Services, the IPBS, the sister to IPCC, the Climate Panel, which for the first time released its global assessment on biodiversity, showing that we are in the 6th mass extinction of species. The first one to be caused by another species, us. One of these 6, by the way, was the loss of dinosaurs on Earth 60 million years ago. We're talking big pace of change. We are moving in a rate of losing potentially 1 million species on Earth over the next decades. We have the data showing that roughly 60% of vertebrates, of reptiles, mammals, and birds having been lost since the 1970s, that we're moving towards a point of potential collapse in terms of fundamental animal species and all the way down to microbes in functioning in ecosystems. You may have read the quite devastating paper that came out roughly a year ago showing that we have lost 40% of insects and we're moving towards a potential collapse in pollinators in many large biomes across the world related to pesticides and industrial developments. So we have two perfect storms here kind of moving in the same parallel interconnected pathway. The global warming challenge and the undermining of the life support systems in the living biosphere, two equally important fundamental changes. So this trend line, the trend lines of exponential rise in pressures, leads to what I would argue being the scientifically most important message to humanity over the last decades, which is that we welcome humanity to the Anthropocene, that we have now entered a new geological epoch. We're leaving the Holocene, the interglacial period we've been in since the last ice age 12,000 years ago, and entering the Anthropocene, anthros for humans, the Greek for anthros for humans, that we are now the dominating force of change, that we surpass the natural variability of extreme shocks like volcanic eruptions and earthquakes and our oscillation in distance to the sun, all of these still occurring, but we now surpass the amplification and the pace of these changes. Now, the Anthropocene is not based on some hypothesis or models. It's based on, as I'm sure you're aware, the observations from the pathway of change over the last 200 years. So what you see here is the classic hockey stick graphs coming from, originally from the International Geosphere Biosphere Program of what has now become Future Earth, the largest scientific community of global sustainability science in the world. On each x-axis here is from 1750 till today. So from the moment that James Watt invented the coal-fired steam engine in the UK and kind of ignited the fossil fuel-driven industrial revolution in the mid-18th century, up until today. On the red side here you see the socioeconomic drivers of change, so population growth, economic growth, and industrial pathway of consumption and production. And on the green side, you have all the implications on the Earth system. And to the top left there, you have the carbon dioxide hockey stick, essentially the only environmental kind of global pressure curve we tend to discuss. But I can assure you, you can pick any curve that matters for our human well-being, and they look the same. You can pick nitrous oxide eutrophication, you can pick deforestation, land degradation, air pollution, sulfur release. You can pick the one that makes me most nervous in the furthest right-hand corner, which is loss of biodiversity. They look the same. Up until a point around mid-1950s, we had problems in many parts of the world, but they were linear and incremental. We had no impact on the big planet. We were still the small, small world on a big planet. Then 1955, 10 years after the Second World War, we're 3.5 billion people. That's the point where we seem to be putting in the high gear of the industrial metabolism of the modern, globalized industrial world. We just move into high gear and off we go into this exponential rise, and we start really, really exploiting all the systems, the cryosphere, the hydrosphere, the biosphere, and the climate system. And we reach the early 1990s. In fact, late 1980s, early 1990s, and that's where we start seeing the scientific publications of first crash points. We see the collapse of cod fisheries out of Newfoundland in the late 1980s. We see the collapse of the Baltic Sea in the late 1980s due to overfishing and eutrophication. We see accelerated ice melt in the Arctic being observed for the first time. We see collapse of freshwater systems in the US because of eutrophication, from clear water lakes to eutrophied dead zones. We pass 350 ppm, roughly 1989. You remember that the first IPCC report comes out in 1992 after adoption in 1990 of the whole framework convention. We move very fast towards observing for the first time real important acidification measures. We start seeing the first evidence of cracks in the system. So it could be that actually we move into the great acceleration in the mid-1950s, but the planet is so big and the world is relatively small, so it's so resilient that it's able to absorb our unsustainable pressures. There is, so to say, a bit kind of cynically, enough fish in the oceans to continue overfishing. There's enough oceans out there to load with heat. There's enough ocean out there to load with metals and microplastics. There's enough rainforest to kind of overexploit the rainforest. There's simply enough resources out there in the big Earth system that it can, so to say, forgive unsustainable pressures and absorb and give the impression that it's not, so to say, hitting back, because it's able, thanks to its resilience, to absorb the pressures. But come early 1990s, that's where we start seeing potentially the first signs of cracks. We come to the Rio conference, we start being concerned, we launch the conventions on climate, on biodiversity and desertification, we start struggling, and then it takes us 25 years before we come to Paris in 2015. And it takes us 25 years to come to the Sustainable Development Goals, which also occurred 2015. Now that's very frustrating, that long time period. But there is a kind of two forgiving factors here, which is one, that it may be, this is not proven yet, that the actual saturation point where we really start having the world dominating the small planet may not occur until we reach the early 1990s. And then there's a second story, which is in a report of the United Nations Environment Programme. You may not have seen it. It's titled Late Response to Early Warnings. And it's trying to map the time distance between scientific findings and societal reactions on environmental challenges. And quite interestingly, it shows that for acid rain, for ozone depletion, for the links between passive smoking and cancer, on air pollution, and potentially also on climate change, the time difference has been 25 years. So the first findings are published, and then it takes like one generation before you really start having insights sinking in the societal fabric. So what if the first findings really being established with the first IPCC report in 1990, but 2015 is 25 years later? What if finally the coin really sank in 2015, and this is the saturation point, not only in terms of pressures, but also in terms of insights, and that we might be at this real turbulent, but though renaissance point, the change point, right as we speak, because now is the time when things are really starting to sink in. And that it is only because it's not until the late 1990s that the planet's resilience capacity really starts cracking, that we start seeing the findings that really, so to say, are of concern, true concern for us humans. So this is kind of the core story around Earth resilience, which of course has a little bit of a paradoxical backside, which is that so unfortunately the planet is so strong that she has been lulling us into a comfort zone, allowing us to shove all our abuse under her carpet and hiding it so we can't see it, which has then cheated us to believe that the planet is so strong that it doesn't matter. We can simply just deliver GDP growth without bothering too much, that we have a linear production model from exploiting to wasting, and that has delayed action for such a long time. That may be the case, but it's just to kind of show that it's not as if we've been shouting wolf for 50 years. Oh no, this science is published for the first time 2007. The proposition of the Anthropocene is actually not even established formally yet. The scientific work is continuing right as we speak. So that's just one first insight. What's then the second insight of science, in my mind, on the global sustainability sphere? Well, it is that if we are putting all this pressure on the planet, if we are now in the Anthropocene, the big question is, of course, what's the desired state of the planet that can support humanity? I will argue that we can answer that question with quite solid science. So solid, actually, that I frame it in this little challenging question: are we leaving the Garden of Eden? Because when we look at the data, this is paleoclimatic data, we can actually start identifying the Garden of Eden. This is the classic graph over the last 800,000 years. You recognize the ice core data from the Vostok ice core. This is temperature variability deviation from the pre-industrial 14.5 degrees Celsius average temperature, and you recognize the 11 or so cycles from glacial periods to interglacial, the Milankovitch cycling back and forth. Each top here is an interglacial. You have the last interglacial, the Eemian, 110, 120,000 years ago, and then we have our current interglacial, the Holocene. And I'll be focusing in just on this last cycle, which is the last Milankovitch cycle, the last 110,000 years. Now, if we pick out this data, it looks like this. If you take the ice core data from Greenland in this case, you have temperature variability on the y-axis, on the x-axis the last 100,000 years. It's picked out deliberately because we've been modern humans on the planet at least the last 80,000 years. This is a scientifically debated area, but that's when we, according to the latest findings, at least as far as I can read myself through the literature, that we went through also the cognitive revolution of being able to truly operate in communities as modern humans. Now, as you can see from the graph here already, just the illustration, this was a bumpy ride indeed for humanity. We were hunters and gatherers, we were a few million people on Earth, and we had, to put it very simple, a rough ride. We had temperature variabilities at times of plus minus 10 degrees Celsius over a decade. In fact, you see that cold point there at roughly 75,000 years ago. It was deep ice age, minus 4 degrees Celsius. The latest genetic assessments point at us being down to less than 15,000 fertile adults on Earth at that bottleneck point. We were most likely hiding in the Ethiopian highlands, one of the last and only resorts for freshwater and biomass, and we were virtually extinct. As you may know, this is the point where there's this theory on the Toba volcanic eruption disaster, which we know today created a 10-year or so winter on planet Earth. That's a debated issue, whether this is what could explain it, but it's just to show that in that deep ice age part, with huge variabilities of climate, we were virtually extinct, very few people living as hunters and gatherers. We leave the last ice age and we enter this extraordinarily stable interglacial period. What do we do? Well, we literally just enter it, and we do the most important invention of all time. I mean, an invention that bypasses the iPhone and computers and the digital age by far. We domesticate animals and plants. We become farmers. We establish ourselves in villages and domesticate animals and plants essentially simultaneously on all different continents on Earth. And that is the extraordinary proof of the beauty and kind of unprecedented stability of the Holocene. Because we domesticate maize and teff and wheat and rice on different continents at the same time. Now, the last time I checked, we didn't have like mobile phones that we could call each other and say, wow, I came up with this great idea, plant a seed and it grows and it's so smart. Oh no, we did this because the Earth established itself and became so harmonious. Every year, rainy seasons came and went in a predictable way. Every year, it became 15 degrees Celsius warmer in spring, and that lasted until October, and then it got cold again. And we could rely on the growing season. So it became worth the investment to start planting seed and domesticating animals. So we became sedentary farmers thanks to the stability of the Holocene. And off we went into the journey that we all know so well, because it was thanks to the invention of agriculture that we could start differentiating our technological know-how into the different strands that takes us to academic disciplines, to take us to the Renaissance and the great acceleration point in the 1950s. Off we go in the great acceleration. We're today 7.6 billion people, committed to 10 billion people by 2050. We're in the modern globalized world, interconnected as humans on this modern planet. And the conclusion from science is therefore as simple as it is dramatic, actually, which means that as far as we know, the Holocene is the only state of the planet, the only equilibrium state of the planet that we know for certain can support the modern world as we know it. We've lived outside of the Holocene. We can be hunters and gatherers. We can go back to the caves if we kind of have this enormous fluctuation of temperature. But as far as we know, the only way for us to secure an ethically and morally responsible world for 7.6 to 10 billion co-citizens is that we remain in the Holocene. So you can see the drama in the story. We're on our way out of the Holocene, rushing towards the Anthropocene. At the same time, we have the scientific findings landing finally from paleoclimatic data from Antarctica to the Arctic that we depend on the Garden of Eden for our future. We will fail on the Sustainable Development Goals. We will fail on the Fourth Industrial Revolution if we do not remain in a Holocene interglacial state. So that is insight 2. We have a reference point for the Garden of Eden. Now, number 3, well, just before that, just to flag to you that what is so unique with the Holocene is that it is in its full natural variability staying within a range, as far as we know, of plus minus 1 degree Celsius. And I put this graph up here because I'm sure many of you, just like me, collide with climate denialists or skeptics now and then, and they love reminding us that, you know, I come from Sweden, for example, they love to say that, well, but you know, in the medieval warm period, the Vikings were growing grapes on Greenland, and that just proved that it's been so much warmer in the past. I mean, what are you worried about with a little degree here or there? And then you have the Little Ice Age, and you have the Holocene climate optimum. There's of course, a lot of fluctuations here with dramatic implications of climatic variability, but all occurred within plus minus 1. All of this occurred within plus minus 1. It just shows us what it means to change the average temperature on Earth with 1 degree. And now we've bumped even past that point. We are at 1.1. So this is the reminder of how we need to cherish and return to recognizing that planet Earth is a small marble that we need to cherish fully. Now, the third and final insight, before taking us to a new framework for sustainable development, is that if we are in the Anthropocene, pushing all this exponential pressure, if we now know the reference point of a desired planet, the big question is, of course, how does she respond when we put all this pressure? Well, up until recently, up until roughly the 1970s, I would argue, because that's where resilience theory and complex systems research and kind of Gaia theory took off, we still thought that the world was so small and the Earth was so large that environmental change occurred, yes, but it occurred linearly and incrementally and thereby predictably. Actually, when you think of it, economic theory is based on this assumption that things change linearly. In fact, you could never have a discount rate as soon as things change non-linearly. It's just always this assumption that things change in an incremental, predictable way. But science is today crystal clear that it's completely the reverse. Long periods of incremental change, when resilience is high, when you have high biodiversity, high redundancy, and you can cope and dampen and absorb, you have incremental change up to a certain point. But when you have eroded resilience, you've saturated systems, a small additional change, like climate forcing or a disease or a drought or a flood, can push a system across thresholds, and you get shifts and feedbacks, the processes that regulate the state of the system, and they can flip over to irreversibly and abrupt shift to a new equilibrium state. And the big nervousness today is that we may be pushing the whole Earth system across a threshold. Because the key message is the following as well. There's a drama here that we depend on the Holocene, and the Holocene is an equilibrium state. It's an equilibrium state. The Anthropocene is where we are today, but the Anthropocene is not yet a state. It's a pressure point. It's an exponential pressure, but we have not yet pushed ourselves out of the Holocene equilibrium. But we have so much knowledge today that systems on Earth can tip over, and these are the systems that regulate the ability of the Earth system to remain in a Holocene state. This is summarized in the following film, which just shows in an illustration the kind of latest summary of the tipping elements we know in the Earth system. Of course, it starts with the permafrost systems and the Arctic sea ice systems that we know can tip over and release and amplify warming. But we also have evidence that El Nino and the Antarctic and Arctic ice sheets, you have the rainforests, you have the Sahel monsoon system, coral reef systems. All of these are tipping elements where we know that they have multiple stable states separated by thresholds where they can, if pushed too far, flip over. A rainforest can irreversibly become a savanna. A savanna can irreversibly be pushed over to become a desert. And this is what takes us to a point where we, for the first time, can combine the climate trajectory and the desired state of the planet with nonlinear dynamics of tipping elements. And this graph, I would argue, is like the most important message to our climate negotiators. Actually, it was presented to Patricia Espinosa and the leadership when meeting already here in Bonn at the COP meeting. And it goes as follows. So what you have here on the x-axis, I think you've started to get used to that now. This is 20,000 years back. On the y-axis is temperature deviation from our pre-industrial level. We leave the last ice age 10,000 years ago. We enter the Garden of Eden, the flat plus minus 1 degree line you have here. This is when we invent agriculture and off we go to our modern civilization. You have our current temperature rise there just to show how quick it occurs. Here you have the Paris Agreement, which is the most fantastic, legally binding accomplishment so far on climate negotiations. But just this visual reminds us that even if we succeed with Paris, it's outside of the Holocene range. That's just an important reminder that even if we succeed with Paris, we're outside of the equilibrium maximum range of the Holocene. Here we have the IPCC assessments of pathways to the future. As you know, we're following this red line, which would take us to 4 degrees Celsius on average by the end of this century. So we are on a business as usual trajectory that is in the worst case scenario. But the key step here is to add to this figure the tipping elements and what are the risks of crossing thresholds. What you see here is the width of these red-yellow columns is the uncertainty range in science, the recognition that science has no precise quantitative numbers of when a system will flip from one state to another, but we're starting to get better and better precision. So what you see here is at what temperature range are we at risk, as far as we know today, of pushing system across tipping points. And I'll just focus on this set of 5 here, because as you see, the scientific evidence dips into the Paris range, which actually suggests that, according to the scientific evidence we have today, already at 2 degrees Celsius warming, we cannot exclude losing, to the furthest left, the dramatic loss of the West Antarctic ice shelf. Here we have a 6 to 8 meter sea level rise at the West Antarctic ice shelf that we just 10 years back thought was very resilient indeed, and more science shows unequivocally that that's not the case. These are much more vulnerable systems. This is ice on rock being lubricated by warming oceans that could, through nonlinear dynamics, release irreversibly big glaciers, the latest one being the Thwaites Glacier, into the oceans. But you also see how Greenland and Arctic summer sea ice and alpine glaciers are all in this uncertainty range. Greenland holding 7 meter sea level rise. But the most dramatic one here is the furthest one to the right, the coral reefs. Because look at that uncertainty range. It is all within the Paris range. Meaning that the conclusion today is that we have, with a very high likelihood, already the first planetary victim. The first planetary victim is that the world's tropical coral reefs, with a very high likelihood, are gone even if we succeed with Paris. Because they're so sensitive to the amplified frequency of bleaching events caused by El Niño events that we reinforce due to the warming of the oceans. So this is where we are today. This is no longer like just a cannery in the coal mine. This is real warnings from the science when you combine the trajectories of the Garden of Eden, temperature average on Earth, with dynamics of tipping elements. So that is why, and there's therefore no surprise, that the global environmental change research community, when putting all these insights together, we are in the Anthropocene, we depend on the Holocene, tipping elements are hardwired. Naturally, two questions arise from this. One is, well, if we are putting so much pressure on the Earth system and we're potentially leaving the state that can support humanity, we must very rapidly know what are the Earth system processes, what are the processes that regulate the state of the Earth system, and secondly, can we scientifically define quantitative boundaries that can give us a safe operating space, that can give us the quantitative guardrails of where are the boundaries within which we have to stay so that we can succeed in remaining in an interglacial state, avoiding that the Anthropocene becomes a state, that we can actually come back and stay in a Holocene-like interglacial state. And that is what took us to the planetary boundary framework. And it was released the first time in 2009, published in Nature. 2015, an update of this work. We scanned off all the knowledge of our complex, self-regulating Earth system, the science in oceans, in climate, in atmosphere, in hydrology, in ecology, and trying to map out what are the systems that regulate the state of the Earth system. And we landed in 9 systems, and we've been researching this and critically assessing this since 2009. And this is the updated graph, and it's ongoing research. And what you see here in green is the safe operating space. We've been able to quantify 7 of the 9. In gray, you see those that are not quantified. I'll come back to that. But what you see here in yellow is what we call the danger zone, which is the uncertainty range in science. So we put in green the boundary at the lower uncertainty range of science and the upper at the higher uncertainty range. So if you would go back to the previous slide, it would be like the width of that uncertainty range of the science. So in yellow, you're in a danger zone, and in red, you've crossed the point where with high likelihood we start seeing shifts that could amplify and make it more difficult to remain a Holocene state. Now, these 9, well, they were published in both Science and Nature. I don't have to dwell on that. But what I would like to share with you is just very rapidly, what are these 9? And in a kind of a very simple working terminology, we kind of internally, within the kind of science community, talk of 3 categories of the 9 boundaries. And the first obvious category are the big 3. These are the systems that have scientific evidence of planetary scale tipping points. They operate at the planetary scale. They're perfectly mixed. And this is the climate system, stable oceans, and the protective stratospheric ozone layer. So these are the kind of the obvious 3 that have also obvious global thresholds. But then we have the 4 boundaries that we call the slow variables, or the biosphere boundaries, the ones that operate under the hood of the machinery of the biogeochemical functioning of the interconnected Earth system. And these are biodiversity loss, land use change, the global hydrological cycle. So we have, and then finally the 2 element cycles of nitrogen and phosphorus, the nutrient loading, which means that we capture the 3 big element cycles: carbon through climate, nitrogen and phosphorus through the biogeochemical boundary, but then also the hydrological cycle of fresh water, the bloodstream of the whole Earth system. And next to these 4 slow variable boundaries, we have 2 boundaries that we kind of, a bit in working mode, just called the aliens. And these are the aliens because they do not exist naturally in the Earth system. They're created by us humans. And this is one boundary that we originally called chemical pollution, that we today call novel entities, because they're all the types of elements and chemical compounds, from nuclear waste to microplastics and loading of heavy metals, but also, of course, the hundreds and thousands of chemical compounds, from endocrine disruptors to persistent organic pollutants, that we have created and that we load into the Earth system. And then the final boundary is aerosol loading, which is all the pollutants that we release into the atmosphere, and that shades and causes changes in heat exchange and solar radiation into the Earth system. Basically, where we humans play volcanoes with the Earth system. That affects, for example, the Southeast Asian monsoon system, and has massive impacts on both heat exchange and water. Now, these 9, there's continuous work on quantifying these boundaries. That's one challenge. But what's very reassuring is that during soon 10 years of the planetary boundary framework being, so to say, in the public domain, there's been no convincing scientific suggestion to add a 10th boundary. And let me just tell you a little bit as a kind of a joke, perhaps, that in 2009, when we launched this, as you can imagine, it was a bit tempting to try and find 10. it was a bit symbolic, that there should be 10 boundaries to guide humanity's future on Earth. So we were always a bit, on the lookout for the 10th one, but unfortunately it does not seem to exist. But likewise, there's been no scientific support to deduct one of them. It's not as if we have painful critique to say, no, there are only 8 of them. So I would say today, with quite a high degree of confidence, that if we can manage these 9, if we can become planetary stewards of the 3 big ones, the stratospheric ozone layer, the climate system, and ocean acidification, if we can handle the biosphere, which is very much about biodiversity, and if we can get a control over our overconsumption related to chemical pollution and aerosol loading, we have a good chance of returning back into a stable, manageable state of the Earth system. So that's basically where the planetary boundary framework today lands. Now, this is all being, let's say, supported by the recent advancements in science, the need of a planetary boundary framework. And let me just go through pieces of that most recent updates before landing in what does this imply for sustainable development and solutions to the future. So now comes one more little diagnostic piece. Now, the planetary boundary framework was launched in 2009, updated in 2015, but just 1.5 years ago, we were able for the first time to really check the planetary boundary framework. Does it really, how relevant is it to avoid that we move towards a disaster point? And that was done in what was called the Hothouse Earth paper, which is, the title is actually the Earth Trajectories paper, where we for the first time tried to answer the following question. If we burn fossil fuels to a point that we reach 2 degrees Celsius warming because of fossil fuel burning, what are the risks that we cross tipping points in the biosphere that could self-amplify warming, not because we do anything, but because the planet loses so much resilience that it could cross tipping points and self-amplify warming. That led to the first time the tipping elements that I mapped out in the previous visual were explored in terms of their interconnectivity between these systems. They are like interconnected domino pieces in a game, and our careful assessment is that at 2 degrees Celsius warming due to fossil fuel burning, we're likely to bump up warming to roughly 2.3 to 2.4 degrees Celsius warming because of permafrost thawing, forest dieback, and reduced CO2 uptake capacity in oceans and soils and forests. And if we reach this 2.3, 2.4, we risk crossing the yellow tipping points of the systems that, as far as we know now, are most sensitive to approach tipping points at the lowest temperatures, that could then interconnect with the next level of systems that seem to be, as far as we know now, more resilient to global warming, but that could then be at risk because we have bumped up warming. And this could lead to what we call a hothouse Earth trajectory with irreversible self-amplified warming caused not by us burning fossil fuel, but because we get a self-amplification in the Earth system. This was, as you may know, translated in German to the Heißzeit trajectory, chosen as the word of the year even in Germany, because it has such significant implications for our future. And it's illustrated in this systems diagram, which I think is quite useful to just remind ourselves just what is at stake. And what you see here is a timeline, and furthest back you have the limit cycles as far as we know it. So to the furthest left you have this Milankovic ice age, stable basin of attraction. You have the little cup there being the Garden of Eden, the beautiful Holocene. And then we often believe that we kind of move along a kind of a stability landscape that is very flat and incremental. But as far as we understand now, that is not the case. That we are at risk of pushing the system down a valley that could start irreversibly rolling the ball down a place that could take us past a threshold where we irreversibly would move towards self-amplified warming. And our big task is to transform and deviate back into what we call stabilized Earth, and we think that the window is still open for this, but it's just open perhaps 1 or 2 more decades in terms of starting to bend that curve in a new direction. The evidence for this is also reinforced by the so-called Anthropocene Working Group. This is the working group that is providing the geological evidence whether or not we can formally call our current era the Anthropocene. So the Anthropocene has not been formally adopted yet, because this is, of course, in the United Kingdom's Royal Geological Society that defines the geological epochs we're in. But here you see more evidence showing that, according to all the trajectories we have, the journey we're following out of the Holocene is very dramatic. We have, a few months after the Heiseit paper, another paper that supports exactly the same notion, which is the first time ever that an attempt is done to check how has temperature on Earth been not over the last 1 million years, but all the way back to 60 million years ago. So this graph covers 60 million years, and what you see to the furthest right here is the IPCC trajectories of temperature rise of the pathways we're following. And in the line I just pressed up there is the 4 degrees Celsius line, the pathway we are at risk of reaching by the end of the century under business as usual. Okay? The yellow line there is the Garden of Eden. And then you have the Pleistocene, goes all the way back to 3 million years. Now, let's just check, if we follow business as usual, reaching that 4 degrees Celsius point there, how far back will we be winding the climate clock? And if you just follow the black line here, you see we're not winding back the clock like 1 million years, which is the Milankovitch cycling you see there in and out of interglacial glacial. Oh no, we are, as far as we know today, at risk of winding back the clock all the way back to the Miocene, 20 million years ago, in the blink of time. That we would, in 150 years, be winding back the climate clock basically to the point where we lost the dinosaurs. So this is kind of proof of the need to really take this seriously. Now, even more recent than that, which supports even more the planetary boundary framework, colleagues at the Potsdam Institute, for the first time ever, was able to run a climate model to simulate temperature variability in and out of ice ages over the past 3 million years. So here you have 3 million years on the x-axis, and then you have temperature variability on Earth. And look at that y-axis again. It's from -6 to +2. -6 is deep, deep ice age, +2 is the warm situation. And look at the graph furthest down, it never exceeds 2 degrees. So from the knowledge we have today, with the latest science, we can say something which we could not even say 2 years ago, that over the past 3 million years, during the entire Pleistocene, average temperatures on Earth have never exceeded 2 degrees. We've been below 2 degrees all the time. So we have been fluctuating. Oh yes, we've had fluctuation. We've had a rough time when in the Northern Hemisphere we were hunters and gatherers and all these variabilities, but we've stayed within a 2 degrees Celsius world, and in the Holocene within a ±1 degree world. This gives enormous support for the need of staying within planetary boundaries. Now, this is further supported, I'm sure you've seen the latest science on the slowdown of the Atlantic meridional overturning circulation, the heat exchange from warm surface waters that flows from the equator and that turns down and releases heat up in the northern Atlantic, sinks to the bottom and flows back, and that this is slowing down, which is another sign of changes due to global warming. That we have the evidence from Antarctica, which I mentioned earlier, that is melting faster than predicted. That we have so much evidence today of shifts occurring that I kind of come back to this, that the 1.5 degrees Celsius report of the IPCC is, in my mind, the most important report ever released. Because for the first time, the IPCC, based on all the scientific evidence, was kind of forced to conclude that 1.5 is a planetary boundary. It does state clearly that 1.5 is not only kind of a cost point for society. It's not as if we choose 2 or 1.5 or 3, depending on what we are willing to adapt to. Oh no, these are biophysically hardwired points that could self-amplify warming. And the clarity in IPCC is dramatic because it says that we have to cut emissions by half by 2050 to be able to reach 1.5. So the green line here is the trajectory we have to follow. You see bending by 2020 roughly, and reaching a net zero world economy by 2050. That's the green line. The blue line there is the 2 degrees Celsius AR5 runs, and the red and orange are the business as usual trajectories. So just showing the bending of the curve that we have to do. We try to translate this into the pathway of solutions. And this was done roughly 1 year back in what has been baptized the Global Carbon Law. We were inspired by the Moore's Law. You remember the Moore's Law, Gordon Moore of Intel, the inventor of Intel, who stipulated as a kind of a self-fulfilling prophecia that the speed in computers would be doubling every 18 to 24 months. And that prophecy has become a kind of a self-fulfilling prophecia of innovation speed in an exponential, disruptive digital industry. What if we could do the same thing in the transformation back to a safe operating space within planetary boundaries? And interestingly, the pathway we need to follow on carbon decarbonization is following a carbon law. The carbon law is just like doubling the speed of computers every 18 months, equally simple. If we cut emissions by half every decade, we follow the pathway to Paris. And that is shown by this graph. Here you have on the y-axis emission of carbon dioxide from fossil fuel burning and land use change. We need to bend the curve by 2020, so this is just a replicate of the IPCC pathways, and the speed by which we need to reduce emissions in that gray curve is roughly 6 to 7% per year of emission reductions, but it also follows quite exactly cutting emissions by half every decade. So if we go from 40 to 20, from 2020 to 2030, 20 to 10 to 2040, and then 10 to 5 with a little residual by 2050, then we are following a pathway that can take us to the right place. I believe that the carbon law of cutting emissions by half could be quite an interesting guide because when you think of it, it is something that is scalable. You know, a country can adopt a carbon law, a company can adopt a carbon law, even you and I can adopt it as individuals. I will now start cutting my emissions by half every decade. That is something we can do, and that can be applied, and if everyone does it, we stay under this curve. But unfortunately, as you know, that's not enough. We also need to shift that brown curve you see there, which is land use change from food production. The food system is the single largest emitter of greenhouse gases, roughly 24% if you include land use change. Food system has to go from a net source to become a very large net sink. That is assumed in all the IPCC scenarios. This is nothing less than an agricultural revolution to shift world agriculture from a net source to a net sink. I won't go through that in detail, but just to say that we have, in many cases, the solutions for that. So it is possible to succeed. But not even that is enough. As you may know, all the scenarios that take us safely back into a safe operating space of planetary boundaries on climate assumes very large negative emissions from CCS and different biological carbon captures and storage. But not even that is enough. We also need to sustain carbon sinks in natural ecosystems. Blue and green here are carbon dioxide uptake on terrestrial ecosystems and in oceans. And if we succeed with all of this, a carbon law on decarbonizing the energy system, an agricultural revolution, investments in technologies for CCS, and keeping all natural ecosystems intact and resilient, if we do all this, we have a 66% chance of reaching towards 1.5. So dear friends, this is nothing less than a global sustainability transformation. Reaching Paris is not about decarbonizing the energy system. I mean, excuse me, Germany, but it's not only about the coal commission. This is about transforming society. This is about reconnecting the world to the biosphere. This is about recognizing that the 3 remaining rainforests, that the ocean systems, that all biomes on Earth are now in need of our planetary stewardship, because now is the time to really safeguard all the remaining ecological functions on Earth. We simply need the planetary boundaries to be able to do this transition. Now, the good news is that this is something that we start seeing in parallel some scalable solution towards. So together with Christiana Figueres, we released at the Global Climate Action Summit in San Francisco last year. You may remember that there was this grand meeting in San Francisco. we released the Exponential Climate Action Roadmap, where we tried to explore the question, can we cut emissions by half by 2030? Can we follow the carbon law the first decade? And we tried to map up as much knowledge and data as we could, and here are just a few highlights, which I find to be many times, even for us, very surprising and positively surprising. On the left hand, you have the number of countries that have actually decoupled economic growth from greenhouse gas emissions. Now, by 2010, that was 49 countries, and 2020 is predicted to be 53 countries. Now, that's quite an interesting number, because 53 is, roughly 25% of the countries in the world. So we're starting to reach a point where a lot of kind of business management analysis shows that when a minority has become large enough and can tip over the logic for the majority. I mean, when novelties and innovation penetrates markets like iPhones and different electronics, you have to come over the valley of death and reach at least above 15% of penetration before you can really have indent at a large scale. It seems that we're now starting to reach that point when it comes to showing that you can have economic development with less greenhouse gas emissions, and that can be something that can inspire other countries to move. And I should also mention that these 50 are not just like the teeny-weeny Nordics in the world. They represent 40% of global emissions, so this is quite significant. On the right hand here, you have the number of countries that have adopted a price on carbon. Again, roughly 50 countries. Now, we talk so much about the difficulty of introducing a global price on carbon, but most science today shows unequivocally, I would argue, and of course I cannot do better than refer to my dear co-director Ottmar Edenhofer at the Potsdam Institute and the Mercator Center, showing so clearly that with the price on carbon of at least 50 euros per ton of carbon dioxide, we would decisively create the incentives needed to start phasing out very rapidly coal and gradually also natural gas. 50 countries has a price on carbon. We did some work with the Project Drawdown to ask the question, sector by sector, can we with current technologies cut emissions by half by 2030? And we showed that with current knowledge, it is actually possible in areas from food to building to industry and energy supply. So it seems to be we've passed the point of utopia. It's not like just a fantasy that we can start scaling in a competitive way of movement towards a decarbonized future for humanity. Just recently, we released the so-called Eat Lancet report that tries to take on the food challenge. So I would argue that there are so many challenges, but there are two dominated ones that we need to take on urgently. One is the energy transition, and the other one is the food transition. The food transition because, as you may know, food is not only the single largest emitter of greenhouse gases, it's also the single largest consumer of fresh water, the single largest cause of biodiversity loss, the single largest cause behind transgressing the nitrogen phosphorus boundaries, and a big culprit when it comes to chemical use, and the biggest land system transformer. 50% of terrestrial ecosystems are transformed to different forms of agriculture. So to put it simple, if we can decarbonize the energy system and transform the food system to sustainable food production, we have quite a big chance of returning back into a safe operating space. The Lancet Commission tried for the first time to ask the question, can we actually scientifically quantify what would be the planetary boundaries for sustainable food, and what would be healthy diets that could potentially contribute to speed up that pace towards staying within planetary boundaries. We took a planetary boundary approach to both health and the planet, defining the planetary boundaries that food is primarily associated with, quantifying these, so defining planetary boundaries for food. What are the guardrails for the food system to be able to stay within a safe operating space? And then we did scenarios into the future, asking ourselves the question, can we feed 10 billion people within a safe operating space, and what would it take? Now, this graph, I won't go through all these scenarios with you in detail. It just requires to show you two key things. So up there you have the boundaries. You recognize them now: climate, land use, water, nitrogen, phosphorus, and biodiversity. And here you have all the tested variants, and on the upper line there is business as usual. So we continue eating unhealthy, dominated processed food. We just continue scaling up the Western diets across the world, and we continue with our current unsustainable production systems. And what happens is, in the top line there, we go into the red on all the boundaries, essentially. So we transgress boundaries and we continue in a very dangerous direction. But if we, in the line furthest down, if we adopt what is called dietary shift here, which is a planetary health diet, which is basically following the health scientists' latest assessment that we need to reduce red meat consumption, we need to increase the consumption of vegetables, fruits, and nuts, go into more unsaturated fats, and thereby adopt what would be a flexitarian diet, a diet that is very similar to the Mediterranean diet. And if we would move in that direction, adopting the planetary health diet, reducing waste by half, and investing in known sustainable intensification technologies for farming systems like conservation tillage, for example, we have a chance of coming back on all the planetary boundaries. So this is just one exercise of trying to show that with a healthy, sustainable food system, we can return back into safe operating space. Just to show that there's more and more evidence that these transitions are possible. And that where we're moving today on food leads to dramatic reductions in food production. This is the first assessment by Dieter Gerten and colleagues at the Potsdam Institute showing that with current production system, if we would stay within a safe operating space, we would have to reduce food production with over 60% if we are, so to say, taking the planet as our first objective and not caring about feeding humanity. But the same analysis shows, just like the Eat Lancet, that with adopting sustainable intensification practices, we can actually increase food production in a very significant way, basically enabling a future where we can both feed humanity with sustainable food production practices. So it's not kind of a lost cause in any way, but to close then in a kind of a final concluding remark here, we still have to return to the fact that the challenge is very large. And this is a paper that came out very recently from Leeds University, from fantastic work, for the first time mapping all the countries in the world, to what extent on the x-axis they are transgressing planetary boundaries, so the further to the right, the more unsustainable you are, but also to what extent these countries are achieving social aspirational goals. And the further up on the y-axis you are, the better is the Human Development Index, the better is longevity and education and economic growth, the more of the Sustainable Development Goals the countries are achieving. And of course you want to be in the upper left-hand corner, good social and economic human well-being within planetary boundaries. But as you see, there's not one country there. The rich countries are up here. This is where Germany is and Sweden. We're still delivering human well-being at the expense of the planet. This is the latest update. So the big challenge is there. We need to transform the logic of modern human well-being back into a safe operating space. We need to get the Sustainable Development Goals to really work for humanity, the framework adopted by all the nations in the world that gives for the first time a roadmap for people and planet. Now is the time to really take that seriously. Unfortunately, most countries that really love this framework kind of do not take it really seriously, and they tend to kind of run with it as I would, just like a bit like a Swedish smorgasbord. You just pick your goodies and you take your favorite goals here and there. You do a little bit of an economics, a bit on gender, and perhaps something on poverty alleviation. Well, I hope that my lecture has shown you that we need to transform this smorgasbord into what I call the wedding cake, which is that 4 of the Sustainable Development Goals, Goal 6 on water, 13, 14, 15 on biodiversity, oceans and climate, are non-negotiable. They are the planetary boundaries. They have scientific targets that define the guardrails for us to have aspirational goals on eradicating poverty, eradicating hunger, having good economic development, having equity, having peace, and all the aspirational goals we need for humanity. And that this is the new definition of sustainable development. In fact, I think there is an argument to say that now we need to transform, we need to move into more exponential transitions towards equitable sharing of the remaining space on Earth, which requires us to redefine sustainable development. I would say it's no longer about reducing environmental impacts. It's no longer about the triple capitals of social, ecological, and human sustainable development in the Brundtland Commission. No, now is the time to take the whole planet seriously and to say that it's about prosperity and equity within planetary boundaries. This is our future. This is what we now need to recognize as the key challenge for humanity. And it means, which I've said a few times now, that I think the mental shift is the dominating one. Let's now kind of reconfigure ourselves. We are no longer this small world on a big planet. We are the big world on a small planet. We need to, no longer just get in awe when we see Earth rise. We need to kind of have Earth rise all the time in our heart, in everything we're doing. And therefore I think that the guiding principle from science is to put the Sustainable Development Goals right inside a safe operating space, and that can be the mental model for success into the future. And I think that is what we now need to really start spreading the word across the world, because quite frankly, the time is running out. Also for me, by the way. Thank you very much.
Thank you very much for this great talk. And now we have about half an hour for Q&A. So if you have a question, please raise your hand, and Florian, our microphone monkey, will bring you the microphone. Let's start on the left there.
First of all, thanks, Professor Rockström, for the really good talk. I would like for you to explain me something like a 5-year-old, if it's possible. You were talking about that we were virtually extinct during the Ice Age. We were down to 15,000. And you said that's based on genetic results. So I can imagine that we could measure that we were inbreeding or something. In the case of the climate clock, if we're calculating the temperatures of the past, it's based on simulations. What exactly is this based on? How do you build all this data of so many million years ago?
Yeah, well, to begin with, of course, I should be very clear that fantastic piece of paleoclimatic research that tries to kind of recreate the temperature record all the way back to 60 million years ago is something that I've not been part of doing, and it's not even at the Potsdam Institute. These are colleagues elsewhere in the world. That work is built on massive different sources of data. So what you see there is, so let's say 1 million years back is direct ice core data, which is giving us the record, very precise records actually today, of carbon dioxide concentration and temperature proxies that can be translated into temperatures in the air. But deeper back from that, there is a whole set of different sources of data, from tree ring data, from different archaeological data that gives points that then models have been used to calibrate against to recreate temperature records in the past. And then when you go even further back, there are different geological methods that I cannot recount even to an adult, if you want to have it by a 5-year-old, to get the precision here. But what we have is a quite interesting ability from deep cores to be able to reproduce epochs. I mean, this is geological research methods that are used from different strata and different biomes and sea cores that can be used to try and recreate these timelines. So of course they have a high degree of uncertainty, but it's quite interesting how they are then matched with different mathematical equations like the Milankovitch equations that show that physics kind of support these estimates from the position of our planet to the sun, for example, and that these are possible to reproduce based on physical equations, which is also very reassuring. So it's not like regression equations, but these are systematic mathematical equations that are deriving from our understanding of how the universe operates. So I would say that these are definitely going to gradually change as science advances, but I think we've got quite a good grasp actually of the large magnitudes. I mean, in terms of, are we talking of 4 or 5 or 6 degrees? I don't think we are so far away from what has been the case in the past. But it's an impressive piece of research.
Okay, could we get raised hands again? Yes, right there, please.
Yeah.
Thank you. Thank you once again for the interesting talk. I have a question. You mentioned that it takes usually 25 years from the first scientific evidence to be transformed into a policy or into a law. And if it will take another 25 years for this new understanding of sustainability to be transformed into real understanding and real policy and law, will we have enough time to catch up to the right track?
No, you're right. We cannot wait one more generation for change, and I think that is, well, to begin with, I think we can potentially hope that what I'm trying to say is that 2015 may actually be a point where the insights are really starting to sink in. So we don't need another 25 years. That even though I think we who live on Earth right now cannot really see how rapidly things are changing, because we feel continuously frustrated with things not really changing at the pace that they should. But perhaps in 50 years' time, when you look back at this time, you might see historic books saying that in 1990 came the first IPCC report, 25 years later the world adopted the Paris Agreement and the SDG Agreement, and then it started to change because that was the 25-year point. We may already have reached it. But you're right that we cannot lean back and say, so things are now settled. Under no circumstance. That's a trick. We are at this very turbulent point. It could actually bounce back and we lose it. I think now is the time to really keep the momentum up, to really ensure that this is the point when the insights sink in. And there will certainly be new insights that may take some time again, but what we also could hope for, I think, is that with the digital interconnectedness we have today, things go faster than in the past. So just look at the Fridays for the Future that have kind of ramped up exponentially, not in a 25-year period, but in a sudden smash. And I think that can also be a positive sign that things can go much faster today, which can be both a threat, but also a potential opportunity.
Okay, let's maybe go to the other side of the room a little bit.
Taking into account the first part of your talk where you say that the next 20, 30, 50 years is going to define the next 10,000, and also picking the example that you show about Bolsonaro in Brazil, and also picking the last part that you say that we have to have a mind shift in the society. Do you think at any point in the soon future is going to be justified to put more value in this mind shift than in other values of the modern societies, such as democracy or freedom?
How do you mean? To go kind of that we would go beyond democracy and freedom, or?
For example, I come from Argentina, so I have a kind of South American mindset, but a lot of things in the history in South America were done by force. So do you think, in your personal opinion, at some point it's going to be justified that this long-term consequence can be above, like at least temporary, these other modern social values, like freedom, democracy, and so on? Yeah.
Well, that's a very difficult question, and I would certainly not claim to have an answer to that. The only thing I can say is what really I think scares me and scares many of us is that the further we go without acting, the more we close in the window for democracy. That I think is quite clear, both in terms of the threats to democracy, because of destabilizing the fabric of societies. When you get more extreme events and more migrants and more conflicts connected to climate change, for example, you put democracy at risk. But also that the further you go, the more we will come into an emergency point where we need so fast action that it's questionable whether democratic principles can be efficient enough to change fast enough. I wouldn't argue that we are at that point yet. I think there's more support for democratic procedures to be the most effective way of getting mobilization towards sustainability, but it's something that, quite frankly, also is discussed and is a worry that, when do we come to a point? I mean, just take, for example, that what if we come to a point where we consume the entire remaining global carbon budget, and the only way forward is to, cut emissions by 10 to 20% per year? Well, then we have to bulldoze down coal-fired plants. Now, how do you do that? How do you force Brazil to keep the entire Amazon rainforest intact? I mean, these are questions that we don't really deal with yet, but the question is when will we be forced to deal with them? So then my tack on that is that it's much wiser to have all the cards on the table, lay the science clear for everyone to transparently see, and have a dialogue on this. I would like to see a planetary emergency declaration be discussed at the General Assembly of the United Nations, for example, so that it's openly discussed at the democratic arenas we have. Then you'll have the Bolsonaros in the world being kind of criticizing this, but at least we can talk about this as a global community. But you're right, this is perhaps one of the most sensitive issues that we may be facing. I don't think we are there yet.
Maybe if I can interject a little question on my own. So, just looking at the fact that we're barely able to enforce taxation on large corporations, do you think we can sort of effectively enforce a carbon budget? Is that a thing? Like, what measures do we have to take to enforce such things?
No, I think we need to enforce a carbon budget and thereby, let's say, a carbon law trajectory for all businesses and countries. I think you need two things. And that's what we're struggling with, actually. But one is a price on carbon. But that won't do it alone. It won't be enough to have just a price on carbon. But you also need to have science-based targets on your emission pathways. So, for example, what Germany is struggling with, actually, to have a climate law that puts a clear trajectory that you need to be at 40% reduction of emissions by 2030, combine that with a price on carbon. So you have the price creates the incentive on the market, and the science-based targets locks the system, so you cannot have rebound effects in other, like just coal going to natural gas. And with those two, I think you can move much, much faster than today. Of course, there's the third element here, which is pull the plug on the $550 billion per year in subsidies to fossil fuel use, which we, paradoxically still have today.
Thank you. So could we get a show of hands again? Yes, could we get the lady in the back, please?
Thank you. Maybe along the previous question, I was wondering, mankind doesn't really have the track record of always going the reasonable way. And I don't see like two options. One would be basically we cut down our emissions, we go the reasonable path and so on. The other one is we don't do anything and hell breaks loose. And then I'm wondering, like with when there's like some invasive species somewhere, then people brought in another invasive species in order to get rid of the first invasive species, and then there's a vicious cycle going on. Is there also some serious crazy plans to tackle, for example, carbon emissions, like, I don't know, pumping some other chemicals in the sky? Is there like another, so you seem basically to have some reasonable plans, but there might also be some, I don't know, depending on the viewpoint, promising aggressive plans.
Oh yes, no, but there are many crazy ideas out there.
Yeah, that's why I'm sure the internet is full of them. That's why I'm asking about the ones that are taken serious.
No, but it's you know, to put it a bit more serious, I mean, it's beyond also crazy ideas on the internet. I mean, there's also the whole geoengineering community. There's a lot of hope by many serious analysts who believe that we can geoengineer ourselves out of this crisis from solar radiation management, which is one of the most extremes, which would be mirrors in space that basically reflect back incoming solar radiation, all the way to having stratospheric airplanes spitting out aerosols that would mean that you would basically imitate volcanic eruptions and create kind of temporary winter conditions on Earth, to fertilizing the oceans to have a radical increase in carbon dioxide uptake. So you have, and then from that you have the more lenient biological carbon capture and storage systems where you would, plant trees en masse, cut them down to produce energy and electricity, and then you put the carbon dioxide back into Earth. So you have a negative emission technologies. So all of this is a research strand. There's no evidence that we can do it. There's only some small pilots. Most of these pilots have failed. In fact, in Germany, they were tested at pilot level to have carbon capture and storage in coal-fired plants. Over several years, Vattenfall, Swedish Vattenfall, were actually investing in this in Germany, but they have been closed, all of them, because they were too costly. So we have the technology actually to, for example, retrofit and take up carbon dioxide from coal-fired plants, but so far nothing is happening, and that's why I think I'm in no doubt today that we will need negative emission technologies or different forms of CCS. I'm very skeptical to the big geoengineering ideas like solar radiation management. The reason for this is that you have so many unexpected negative side effects. I mean, if you would load more carbon dioxide in the oceans, it leads to sabotaging even faster or marine life because of ocean acidification. You have so many negative side effects. And when you think of it, what if we would start putting up mirrors in space? Who would control them? Who would decide tomorrow morning you have the shade, and you get the sun? It's like it's quite a complicated venture to start manipulating the solar radiation on Earth. So I think all of these are in the space of high risk utopian, and that's why I would like to emphasize technology where we work with nature rather than work against nature. And one of the most promising is, of course, to maintain the resilience in ecosystems. And I do see that we will need to use biological systems for carbon capture and storage, what is called BECCS. I think that is unavoidable. To really have energy forest systems that take up carbon dioxide for photosynthesis, we produce electricity with that biomass, and in the production system we capture up the carbon dioxide and plug it back into the soil or into the bedrock. And that this is criticized to a very large extent because all the water and all the land and how it can compete with food. I mean, there are so many concerns. Again, the planetary boundary framework is a way of forcing us to have a systems approach here, that you don't go down one route to solve the climate boundary and destroy the other boundaries. But I think we are inevitably in a space where different forms of geoengineering has to be discussed seriously. We cannot, just 10 years back, I was among them who said, geoengineering, no way. But I think today we have to consider it more seriously to understand it.
Thank you. Okay, could we get another show of hands, please?
Yeah. Again, thanks for the nice talk. From your plots that you showed, it became very, very clear that the Holocene has been an era of very stable Earth system. Is it known how that happened? Like, was there some lock-in mechanism that kind of was able to lock the Earth system in that channel? And is that something we could specially safeguard? So why did it happen? Why did it become so stable as compared to the years before that?
Yeah, no, that's a very good question, and the answer is actually we do not know for certain. There are many scientific discussions around that. I should say that also which is of course quite important, that as far as we know today, if we are successful to stay within the Holocene, we would have another 10-15,000 years in an interglacial before heading back into a glacial period. So it wouldn't go on forever, but it would still be another 10-15,000 years. Now, why is the Holocene so stable, even more stable than the previous interglacials? Well, to begin with, one should say that interglacials are in general quite stable, so the glacial periods are more variable than the interglacials. But still, the Holocene is particularly stable, and as I have not been able to, in any of the scientific interactions we've had a convincing story of why. But there are a few hypotheses. I mean, one is that if you look, and I think it comes back to the first question, if you look in that 60 million graph, you can see the general trend line is like the Earth system is gradually calming down. It's like it's a bit like a system that you start bouncing and then gradually it just settles in gradually more and more. So it could be as simple as just being that the Holocene is at the tail end of a long journey, and that is simply calming down. Okay, that could be one. But then there's another more exciting hypothesis, perhaps, that the fact that we started manipulating the Earth system and that we humans had little doing in this, that perhaps the beginnings of our Anthropocene impact in turn kind of helped to give some feedbacks that stabilize the system. But there's no models or no analysis that really can validate that. But there are actually those who mean that the Anthropocene did not start in the 1950s. It started 8,000 years ago when we invented agriculture, because we've been kind of manipulating the planet for 8,000 years. So that could be another potential explanation, but I'm much more of the view of this calming down trajectory, actually. I should also say, which is, I get sometimes the question, isn't there anything positive with global warming? There must be something that is good. And the answer is no, there's nothing that is good. I mean, just to reassure you. But when I was sitting with Richard Branson once, and he was really forcing me, you need to tell me something positive. And one potentially cynically positive thing is that a paper that was produced by colleagues at the Potsdam Institute a few years back showed that very likely we have loaded the atmosphere with so much energy by fossil fuel burning, so our warming is so significant already that we will very likely never more return to an ice age. That we've kind of stopped that window. So we may forever be in a Holocene type state. So if we avoid the Hyzite, we could even avoid the ice age, and we would have infinite harmony. Yeah. So that's if you want a good story, that's
That sounds great. Right, a gentleman in red here, please.
Thank you very much to get me a bit emotional. I have first one question. High temperature carbonization, what do you think of it? Is it dangerous or something like that? Has it negative effects? High temperature carbonization.
high temperature decarbonization?
No, not decarbonization, carbonization. It's a very way to get carbon fixed.
Okay, you mean to use high temperature for fixing carbon?
Yes, and pressure.
Yes.
You don't know this method.
I do not know what the implications could be, no.
To avoid CCS. Because I think CCS is dangerous, and I understand the people who didn't want it in the region, and I think there is a method to make it without CCS, to fix carbon without CCS.
No, I'm really excited about it. I mean, there are several research frontiers of using different physical and chemical approaches to fixing carbon dioxide directly from the atmosphere. And I do not know those systems, but I'm really excited about that there are different avenues of exploration there.
Sorry, I didn't understand your last words. Can you speak a bit, not a bit slower, please?
No, so I do not know of these technologies.
Yes.
I think it's promising to explore them. I think it's good to explore them.
Yes. Okay. Okay.
Thank you. I think maybe you can also discuss this further afterwards. But could you maybe remind a poor theoretical physicist what CCS stands for?
Carbon capture and storage.
And why do people not want it in their region?
So just the carbon capture and storage are different technologies to basically take carbon dioxide out of, for example, a coal-fired plant, liquefy the carbon through pressure, and then plug it back into the Earth's crust. Now, the reason why that is criticized is the risk that you may store it, but you may also release it and have deaths of human beings because of carbon monoxide toxification. So it's a technology that is not obviously secure. I think that is one of the main concerns. Now, one should say that oil industry have been using that technology for decades and decades and decades because they use carbon dioxide liquidification as a way of keeping the pressure up in the oil exploration tubes they have. So when pressure is reduced, they use concentrated carbon dioxide in their oil extraction technology. So it's a known technology, but we have never used it to simply just trap carbon dioxide and put it back into the Earth's crust. But you're right that there's a lot of debate around CCS. And but I think it's something that needs more research and development.
Okay, thank you. Could we get another show of hands? Yes.
Thank you, Professor Rockström. In your very interesting lecture, I missed one point. I don't think, or either I missed it or you said it, but I didn't hear it, about the effect of human population, the amount of human population, which has been rising all the time until recently, after in Europe at least, after the baby boom, the amount of inhabitants in Germany, for instance, has gone back. And in China, even they had a law by which people were not allowed to have more than one child for some decades. In other countries where the economy isn't so well developed yet, we have a very high rise of population. So is that a factor which may also be of significance for the problem that we are talking about?
Yeah. No. Thanks for that question, and you did not miss it because I didn't mention it. There is actually a reason why I didn't do it, and it's, so to say, on purpose, which is not that I don't find population growth to be a concern, but it's the following, and I here actually rely quite heavily on the late Hans Rosling, a close friend and colleague of mine who passed away quite recently, as you know, and he showed very convincingly, and I think this is key, that we have already passed the demographic transition point, so the number of births on average per woman is going down. It's at 2.1 in the world today. It's only a handful of countries that are above 4 or 5 children per woman, and that, most importantly, the demographic transition goes very slowly. And that between now, 2019 and 2050, it's very difficult to change and influence the population curve. So to put it simple, in his words, the girls are already born today who will be giving birth over the next decades, which means that our task in population dynamics is to avoid becoming 11, 12 billion, but it's very difficult to avoid 10 billion. It's really difficult. From the step from 7.6 to 10 is largely already committed in terms of girls being born, cultures changing slowly, and the reason why we become more people is predominantly that we live longer. So it's a change in the demographic pyramid, and it's very difficult to change that. I mean, that's part of development. And then finally, the kind of nail in the coffin in a way is something that we know so well, which is that the major driver behind threats to the climate system is predominantly driven by the rich minority in the world, not the poor majority, and all population growth occurs in the poor countries in the world. So the big danger is that the poor countries adopt Western lifestyles and that they accumulate to a point where everyone is rich and everyone is contributing to global warming. That would be like the nightmare. But so far, it is quite honestly, it's us in Europe, it's North America, it's the OECD countries, and we have already transitioned. I mean, we are at 1.6, 1.7 average children per woman. So your point is right. We need to do everything we can to balance population. But I think, to put it simple, for our task, the task we are facing now, which is to cut emissions by half in the next decade, I think there's not so much we can do. On the other hand, we need to put girls in school now because it's a slow variable. I mean, that's the, and by the way, that's the proven methodology. Put girls in school, and you reduce the demographic curves, and that is the pathway. So you're right, but at the same time, I think it wasn't like I just forgot it, that I didn't mention it.
Could we get another show of hands, please? Yes, her, please.
So there's this very popular opinion about veganism, that it's saving the environment. And would you consider vegan diet as a possibility to slow down global warming even more than, for example, adapting a flexitarian diet?
Yeah. Well, so my simple answer is no. But let me qualify it a little bit. But I have great respect to those who choose a vegan diet. I think it's something that I respect. But I'm absolutely convinced that will not take us to the future we need, because to begin with, we cannot have all people in the world becoming vegans, because we have to recognize that we have 3 billion small-scale farmers in the world that all depend on the little single goat or small pens of hens and some little livestock that is that is really the basis for their limited livelihoods, and that animal protein plays a role in so many cultures in the world. So a reduction in animal protein intake is really important, but going all the way to vegan, which again I respect, it's the kind of the most drastic move, but I don't see everyone doing that, and I would find it a much more realistic pathway forward to say that, look, why everyone should be interested in having the best possible health, and a healthy diet is a diet that has drastic reduction in red meat, but you don't necessarily have to go all the way to the vegan diet. On the other hand, I think veganism can be a bit like environmentalism, a good reference point that can draw the mind shifts in a new direction. So I think it's something that is respectful, but not necessarily the only solution. And then also, I should also just add that even though eating less meat is really important, we tend in the media debate kind of exaggerate that as kind of the only issue. It's like now suddenly that's the only issue that matters on if you want to do something with climate, stop eating meat. But that is just a small partial issue. I mean, it's much more important to stop driving diesel guzzling cars, and so we have to be clever in our ability to balance this as well.
Okay, so now we are outsourcing the task of finding a nice, short, poignant last question for this session. You.
You were talking about another solution. So what would you think about culturing meat?
About?
Cell culturing for growing meat in vitro.
Okay, you mean using kind of laboratory-based meat production? Yeah, I think it's a niche. It's an interesting niche, but I don't see that scaling to a kind of a large solution. And I think that is something one has to recognize, that the natural systems have evolved over millions of years and are really efficient and really impressive. I mean, that's something one has to recognize, that the photosynthesis is extraordinary. And I think it's really important to have biogeochemical process that tries to imitate that and learn from that to create new energy systems. And potentially there's a niche market for artificial meat, for example, but I think it will always be a small niche product for an urban elite, essentially. But again, it's not wrong to explore that. It's like Formula One technology has spilled over technologies for normal vehicles. I think that can also spill over with insights that are kind of interesting. But I don't think it's the solution. Do you like it? Yeah.
She is nodding for the cameras. Okay.
That's impressive. Yeah.
Do you have some closing remarks?
No, just to say that thanks for all these really insightful questions, and I really want to come back just where I started. I think it is a moment in time that, of course, requires the insight of there's reason to be really concerned, but it's also reason to be very excited about the fact that the turbulence we're seeing is also a typical sign of being in a transition point, and that this transition point, I think, has a lot to do with now that we're entering an era where sustainability is kind of increasingly the pathway to the future. And let me just give you one little, perhaps insignificant, but I think it is symbolic actually, that if you may not have read it, Harley Davidson, I mean the heavyweight motorcycle company, is going electric in August 2019. And yeah, and I mean when in my mind when Harley Davidson goes electric, the big Hells Angels, oil smelling, big guzzling, really loud motorbikes are seeing that their only future is electric. I think that is a symbolic step, and it just shows us that sustainability is no longer about, giving up and sacrificing and going back to the caves and stop living. It's really about turning a corner towards something that is better and more healthy and more just and more technologically advanced. So let's go the Harley Davidson route. I think that's one part of the message today as well.
Thank you. Please give our speaker a warm round of applause.
Thanks.
Okay, and while we